Lesson 21.2, Analyzing Decisions. Essential question: how can conditional probability help you make real-world decisions? You can use a two-way table and or Bayes' theorem to use given information to calculate a conditional probability. Then you can use a conditional probability to evaluate a decision that may have been based on the given information. Okay, so let's see here. You can use a two-way table. You can use a two-way table and or Bayes' theorem to use given information to calculate a conditional probability. Then you can use the conditional probability to evaluate a decision that may have been based on the given information. Analyzing a decision using probability. Scientists have developed a test that can be used at birth to determine whether a baby is right-handed or left-handed. The test uses a drop of the baby's saliva and instantly gives the result. The test has been in development long enough for scientists to track the babies as they grow into toddlers and to see whether their test is accurate. About 10% of the babies turn out to be left-handed. Okay, that's key information right there. 10% of the babies turn out to be left-handed. The scientists have learned that when children are left-handed, the test correctly identifies them as left-handed 92% of the time. Also, when children are right-handed, the test correctly identifies them as right-handed 95% of the time. In the first year on the market, the test is used on 1 million babies. Okay, so 1 million babies. Complete the table. Begin with your grand total lower right table cell and the row totals, and then use them to help fill in the four actual versus test cells, and then the two column totals. So, all right, 10% of the babies turn out to be left-handed. Well, 10% of 1 million is 100,000. So that means that 900,000 are right-handed, actually right-handed, right? Okay. Now it says left-handed. Let's see. The scientists have learned that when children are left-handed, the test correctly identifies them as left-handed 92. So test left-handed and actually left-handed is supposed to be 0.92. Well, 0.92 times 100,000 is going to be 92,000. Okay, which means 100,000 minus 92,000, that means 8,000 will test right-handed, but they're actually left-handed. Okay, good. Now, let's see, it says the test, let's see, also when children are right-handed, the test correctly identifies them as right-handed 95% of the time. So let's put test right-handed and actually right-handed. That's going to be 0.95, and that's going to be 855,000. All right, 900,000 minus 855,000 is going to be 45,000. All right, now if we add these two right here, we get 137,000. You add those two right there, you get 863,000. Okay, and if you add across there, that should be 1 million. All right, good, good. What is the probability that a baby who tests left-handed actually is left-handed? So let's see, that was 92,000 divided by 137,000. And that's approximately 67.2%. Okay, and that's based on the table. What is the probability that the baby who tests right-handed actually is right-handed? So that was 855,000 divided by, and that was right here was 863,000. 863,000. And that's about 99.1%. All right. Is the test a good test of right-handedness? Well, at 99.1%, I would say yes. Yes. 99.1% is a reliable indicator that the baby will be right-handed. All right. A baby is tested, and the test shows the baby will be left-handed. The parents decide to buy a left-handed baseball glove for when the baby is old enough to play baseball. Is this a reasonable decision? Well, let's see. What is the probability who tests left-handed actually is? That's 67.2%. That's 67.2%. So I would say no. The test is correct 67.2% of the time. When the result is that the baby is left-handed. So if the test says the baby's right-handed, that's pretty, 99.1. But if it says it's left-handed, might ought to be careful about that. Describe two ways in which the test can become a more reliable indicator of left-handedness. The obvious way is to improve the test so that it is better than 92% for babies who are actually left-handed. But the better way is to improve how the test works on right-handed babies so that there are fewer cases of right-handed babies who test left-handed. Let's see here. The obvious way is to improve the test so that it is better than 92% for babies who are really left-handed. But the better way is to improve how the test works on right-handed babies. So that there are fewer cases of right-handed babies who test left-handed. All right. Deriving Bayes' theorem. Bayes' theorem gives a formula for calculating an unknown conditional probability from other known probabilities. You can use Bayes' theorem to calculate conditional probabilities like those in steps B and C in Explore 1. Complete the steps to derive Bayes' theorem. Write the formula for the probability of B given A. So that's going to be probability A intersection B divided by the probability of A. Solve for the probability of A intersection B. Well, from the previous lesson, we learned that is the probability of A times the probability of B given A. Write the formula for the probability of A given B. That's going to be the probability of A intersection B divided by the probability of B. Substitute the expression for the probability of A intersection B in step 2 into the formula for probability of A given B in step 3. So the probability of A given B equals the probability of A times the probability of B given A over the probability of B. Okay? Probability A times right there. And we put that in place for here. Okay. Complete the equations at the bottom of the tree diagram. Use the fact that the probability shown along each branch is a probability of a single event to which the branch leads. Each product of probabilities listed at the bottom of the tree diagram is the probability that two events occur together. All right. So you have the probability A, probability of A complement. Okay. Probability of B given A, or the probability of B complement given A. Well, probability of B given A times the probability of A equals the probability of A intersection B. All right, probability of A times the probability of B complement given A will equal the probability of A intersection B complement. Okay. So now we have probability of A complement times the probability of B given A complement. That's going to give you the probability of A complement intersection B. And this will give you probability of A complement intersection B complement. Okay? Remember up there, probability of A times the probability of B given A was probability of A intersection B. Complete the explanation for finding the probability of B using the tree diagram in step B. Because events A and A complement are mutually exclusive, the event A intersection B and A complement B are intersection B are mutually exclusive. Since the union of A intersection B and A complement intersection B is B, the probability of B equals probability of A intersection B plus the probability of A complement intersection B, which equals probability of A times the probability of B given A plus the probability of A complement times the intersection of probability B given A complement. Use your results from step C to rewrite your final expression from step A to get another form of Bayes' theorem. So the probability of A given B equals the probability of A times the probability of B given A over the probability of B. This equals the probability of A times the probability of B given A over the probability of A times the probability of B given A plus the probability of A complement times the probability of B given A complement. All right. That seems kind of confusing at first, but let's look at it here. Number 4, explain in words what each expression means in the context of Explore 1. Probability A is the probability of actually being left-handed. Probability B is the probability of testing left-handed. Probability A given B is the probability of being left-handed. The probability of being left-handed if the baby tests left-handed. All right, probability of B given A is a probability of testing left-handed. If the baby is left-handed. All right. Use Bayes' theorem to calculate the probability that a baby actually is left-handed, given that the baby tests left-handed. Explain what this probability means. Remember the probability of A, the probability of being left-handed is 0.10, 10%. Also remember that the probability of B given A is 0.92%. The probability of testing left-handed, given that they are left-handed, is 0.92. Okay, so the probability of B, and that would have been 137,000 over 1 million, is 0.137. So the probability of A given B is the probability of A times the probability of B given A over the probability of B, which is 0.10 times 0.92 over 0.137, which is 67.2%, which is about 67% of the time a baby who tests left-handed will be left-handed. So you might not want to go out and buy that ball glove just yet. Using Bayes' theorem. Bayes' theorem is a useful tool when you need to make or analyze decisions. Given two events A and B, the probability of B is not equal, and with the probability of B not equal to 0, the probability of A given B is the probability of A times the probability of B given A divided by the probability of B. Another form is the probability of A given B equals the probability of A times the probability of B given A divided by the probability of A times the probability of B given A plus the probability of A complement times B times the probability of B given A complement. Okay, so suppose Walter operates an order filling machine that has an error rate of 0.5%. He installs a new order filling machine that has an error rate of 0.1%. The new machine takes over 80% of the order filling task. Right, so you go ahead and do A, and when you get back, we'll do B together. B, Walter needs to increase capacity for filling orders, so he increases the number of orders being filled by the old machine to 30% of the total orders. What percent of errors in filled orders are made by the old machine? Is Walter unreasonably increasing the risk of shipping incorrectly filled orders? Okay, so what do we got? Well, we've now increased this to 30%. All right, so that makes that 70%. Now, this had an error rate of 0.005, and this had an error rate of 0.001. Okay, so if this is 0.005, that means this is going to be 0.995, and that's going to be 0.999, right? 0.3 times 0.005 is going to be 0.0015. 0.3 times 0.995 is going to be 0.2985. 0.7 times 0.001 will be 0.0007. 0.7 times 0.999 is going to be 0.6993. All right. Find the probability that the order was filled by the old machine. The order was filled by the old machine. Given that there's an order in filling, there is an error. There is an error in filling the order. All right. So we're going to find the probability of old given an error. Okay. So let's see here. Use Bayes' theorem. So the probability of the old machine given an error is going to be the probability of the old machine times probability of an error given the old machine over probability of an error. Okay, so probability old, that's going to equal 0.30 times an error given the old machine. That's going to be 0.005, 0.005, and we're going to divide that by the probability of an error. So that's going to be 0.0015, 0.0015 plus 0.0007, 0.0007. So we have 0.0015 divided by 0.0022. That's 15 over 22, which is 68%. All right. Describe the result of making this change. Describe the result of making this change. Given that there is an error, given that there is an error, the probability is about 68%. Is about 68% that the old machine filled the package. All right. Making this change increases the probability of an error from 0.001 to 0.0008, which is 0.0018. let's see. Well, the old way, let's see, the old, before, let's see, before the error rate before, the error rate before change was 0.001, and 0.0008, which is 0.0018. Before change, and then after change, the error rate is 0.0015 plus 0.0007, which is 0.0022. Okay, a difference of about a difference of about 0.0004, which means that there are 4 additional errors for every 10,000 orders. So it seems like a worthwhile risk. 4 more errors for every 10,000 packages. I would say they do that. Given that the old machine fills so few orders, how can it be responsible for more than half the errors? The error rate of the old machine is 5 times the error rate of the new machine. That's why. In the situation described in Explorer 1, suppose the scientists have changed the test so that it now correctly identifies left-handed babies 100% of the time and still correctly identifies right-handed babies 95% of the time. Well, let's go back. Let's see here. So actually left-handed was 0.10. Actually right-handed was 0.90. 90% are right-handed, 10% are left-handed, right? So test left-handed, that would be 1. So that's going to be 0.10. Well, that's going to give you 0 here and 0 there. All right, because 100% of the time, all right, good. 0.05, 0.95. 0.9 times 0.05 is 0.045. 0.9 times 0.95 is 0.855. Okay, so we completed the tree diagram. With the new test, what is the probability that a child who tests left-handed will be left-handed? How does this compare to the original test? All right, let's see. We'll say probability of actually left-handed given test left-handed and that's going to be 0.10 times 1 divided by 0.10 plus 0.045. So that's going to give you 0.10 divided by 0.145, which is 69%. So the probability that the test is correct in this case increases from from, and it was 67.2% to 69%. Okay, and that's up 2 percentage points. With the new test, what is the probability that a child who tests right-handed will be right-handed? So we're going to have probability actually right-handed given they test right-handed. All right, and we'll get that straight off the thing. 0.90 times 0.95 over 0.10 plus 0.045, and that's going to be 0.855 divided by 0.855, which is 100%. All right. Before it was 99.1%, so increases to 100%. All right, not too bad, about 1 percentage point. Discussion. Compare the probabilities you found in Explorer 1 and your turn 8 and 9. Why did the probability that a baby who tests right-handed actually is right-handed become 100%? The perfect accuracy of the test for left-handed means that there are no left-handed babies who are misidentified by the test as being right-handed. So all babies who test right-handed actually are right-handed. So the perfect accuracy for the left-handed test means that there are no left-handed babies who are misidentified by the test as being right-handed. Okay, the perfect accuracy of the test for left-handed means that there are no left-handed babies who are misidentified by the test as being right-handed. So all babies who test right-handed actually are right-handed. But there are still some babies who test right-handed and actually turn out to be left-handed. So that's where it's a little bit different. How can you use probability to help you analyze decisions? Like we said at the very beginning, you can use a two-way table. So you can use a two-way table and or Bayes' theorem to use given information to calculate a conditional probability. Then you can use the conditional probability to evaluate a decision based on the given information. And when you make your decision based on information that is presented, you're taking the guesswork out of it, and you're putting the probability in, putting it into something that you kind of do informally in your head, and a lot of times you can make a better decision. Great lesson, folks. I'll see you tomorrow in class, and you have a good evening.